In the last of this short series of videos about the effect of the individual terms in the frequency response, we'll be looking at the effect of poles. The pole terms, you may remember, occur in the denominator of the frequency response equation, and they take the form 1 over 1 plus j omega over minus p. Again, I'm choosing to write minus p because when we determine what these pole values actually are, we'll almost always find that they're negative. If we express the effect of poles in terms of their decibel contribution to the amplitude response, that would give us minus 20 log 10 of 1 plus j omega over minus p, and it's the modulus of that lot. So it's exactly the same form of equation that we got for the zeros, except that there's now a minus sign on the output because the pole terms were in the denominator rather than the numerator. So the analysis works exactly the same as before, it's just that the graph that we get is upside down. But once again, we can consider low frequencies, where omega is much, much smaller than the modulus of the pole there, and therefore this term is much, much smaller than 1 and can be neglected, and that just gives us minus 20 log to the base 10 of 1, which is 0 dB. So the pole is having no effect when the frequency is a long way below the modulus of the pole. On the other hand, at high frequencies, where we make the opposite assumption, and we can neglect the 1 because it is so much smaller than the j omega over minus p term, we'd end up with minus 20 log 10 of the modulus of j omega over minus p, and that's minus 20 log 10 of omega over the modulus of p. Again, I have to keep writing the modulus of p because the p's are usually negative. Both of these are straight lines if you plot them on a graph of gain in dB against the log of the frequency, just like they were for the zeros. And just like they were for the zeros, we can extrapolate those straight lines to find a break or corner frequency there. And that break or corner frequency is going to occur where the high frequency approximation and the low frequency approximation give the same result. This is going to occur when log 10 omega over mod p is equal to 0. In other words, omega over mod p is equal to 1 because the log of 1 is 0, or omega is equal to mod p. And again, just like in the case of zeros, for frequencies a long way below this break frequency, the pole has no effect at all. For frequencies a long way above this pole frequency, the pole's effect is to drop the gain by 20 dBs per decade. We can see that by writing this high frequency approximation in a slightly different form. Gain of dB is minus 20 log 10 of omega plus 20 log 10 of the modulus of p, using the property of logarithms that log of a over b is log a minus log b. And this is the equation of a straight line, y equals mx plus c, where our x-axis is the log of the frequency, and now the gradient is minus 20. So here we're going down at minus 20 dBs per decade. And that's the effect of the poles. You may be wondering at this point why we haven't covered the case of poles at 0 Hz. And the answer is because they don't happen. If we had a pole at 0 Hz, then our frequency response would be of the form G times some zeros possibly divided by j omega. There'd be a term in j omega that I could extract from all of the terms in the denominator polynomial. But that would imply that at very low frequencies, at DC for example, where omega equals 0, the frequency response would be infinite. And if you have an infinite gain at DC, then it would imply that as soon as you turn the circuit on, the output would head off to infinity. It's not an interesting case, and we're not going to come across any examples of this in this module. Now we've seen what the effect of all the zeros and the poles are individually, we can put this information together and produce a very useful technique for quickly estimating the amplitude response of any circuit. It's called the Bode approximation, and I'll introduce it in the next video.